Hey everybody, welcome. We're going to be doing our 10.4 add notes here with ratios. So pretty simple one to add. We have a couple different things. So when we talk about ratios, we have a couple different ones. So I'm going to kind of list out the three main types that we have, but we're really going to focus only on mainly two. Okay, so we have what's called A to B. We have a squared to b squared, but then we also have a cubed to b cubed, and we're not really going to see this one yet until we hit volume. But this is 1 dimension, 2 dimension, and 3 dimension. So we can convert back and forth between these two using by squaring things, or square rooting things, or cubing things, or cube rooting things. So this one right here would be called, usually we call it perimeter ratio or scale factor, right? So it's just one side to another. Okay. Then we have a squared to b squared, which we call area ratio. And then our last one is volume ratio. Now we're writing this down now because it's going to come up, but in reality we really won't see this one in today's lesson. We're going to really focus on perimeter ratio and area ratio. And we can convert back and forth between these. If we're given perimeter ratios, we can square them to get to area ratios. And if we have area ratios, we can square root them to get back to perimeter ratios. Alright, so very simple one today, but that's basically what we're looking at, and we'll see how it works in our 10.4 worksheet. So here we go. Okay, so 10.4 worksheet says the figures in each pair are similar. Compare the smaller to the larger, so we're going to go small to large. Give the ratio of the perimeters and the ratio of the areas. Okay, so ratio of the perimeters to ratio of the areas. And 1 second, I'm just going to plug in my computer. Okay, so we're going to go small to large here. So we want the ratio of the perimeters to the ratio of the areas. So when it says ratio of the perimeters, this is when we're talking about A to B, so we're talking about really single dimension, and then when it says area ratios, we're talking about 2 dimensions. So what we're going to do is we're going to do both. So we have 6 to 8, so we're going to put 6 over 8, small to large. We're going to simplify this to become 3 to 4. So that's my perimeter ratio. We'll call that the A to B. And then to get the a squared to b squared, we just have to square this. So we're going to square that to get 9 over 4 squared, which is 16. And those are our two answers. Okay, 3 to 4 and 9 to 16. Again, next one, we have 3 to 6, so we put small over large. We want to reduce that to become 1 over 3. That's my a to b, so that's my perimeter. And we're going to go ahead and square that to get the area of the ratios, which is still going to be 1, but then we get 9. And just for reference point, I'm going to do this. The perimeter is going to be the yellow, A to B, and the area of the ratios I'm going to put in orange, which is going to be this piece right here, A squared to B squared. So first thing, again, we do small to large, reduce. That's our A to B, and then we square it. So 10 to 15, we have 5 that goes both into that, so that's 2 to 3. So that's my A to B, and then we're going to square it. That's going to be 4 to 9. Over here, we're going to have 8 to 20. Let's see, what goes into the 8 and 20? Is 4 the smallest? That would be 2 and 5, I believe so. 2 and 5, so that's my A to B. So a squared to b squared is going to be 4 to 25. So there we go. Again, perimeter ratio is just my single dimension. So it's just a simplified radical of that one side. And then we square it to get that one. Alright. Each figure, or the figures in each pair are similar. The area of one figure is given. Find the area of the other figure, round to the nearest hundred. So here's where we can get the A to B, but we want the A to B ratio so we can set it up. So we're going to go, again, I'm going to go smallest to largest. We get 4 to 8, which becomes 1/2. So that's my A to B. But since I'm given an area, okay, and that's the smaller, so that's going to go on top. So we're going to go small to large. So I get 12 on top. I don't know the area of the other one. But we want to set this equal to a squared and b squared. So a squared and b squared is going to be 1/4. So we're going to plug in 1/4. Then we can cross multiply, and we get 4 times 12, which is going to be 48, equals x, and that's basically the answer. Same thing over here, area the smaller to the larger. So first I'm going to take the small over the large, and I'm going to reduce this. 14 and 21 both go 7, so that's going to be 2/3, so that's my a to b. I'm going to get my a squared to b squared is going to be 4/9. So I'm going to use that guy to help me solve this. So 4 to 9 is the ratio of small to large. I have 72, which is the smaller area, over the large. Cross multiply, we get 4x equals 9 times 72. So we just have to multiply that. 9 times 72, which is 648, and then we're going to divide by 4. X equals 162 square feet. So again, our principle here is we get our a to b, we get our a squared to b squared, we can use that to set up a proportion to find my missing piece. Okay, let's do 2 more. I'm going to continue going small to large because we've kept that pattern. 8/24 is going to become 1/3. And then we want, that's my a to b, and then we want 1/9 is my a squared to b squared, just by squaring it. So we take 1/9 equals, 135 is the larger, so I did small over large, so I'm going to put 135 on the bottom, x on the top, cross multiply, we get 135 equals 9x. Take 135 divided by 9, we get x equals 15. So the area of the other one is 15 square meters. Alright, area of the smaller rhombus is 60, so again we're going to go 6 to 15. Looks like 3 will go into both of those to be 2 and 5. So that's my a to b. And my a squared to b squared is going to be 4 to 25 equals, and again now I'm going small to large, and the smaller is 60, so 60 goes on top over x, cross multiply, 4x equals 60 times 25, which is 1500, divide by 4, and we get 375. That's going to be in square meters. And we can see that kind of makes sense. It's going to be a much larger area because this is a much larger shape. Okay, so this says find the ratio of the perimeters for each pair of similar figures. Compare smaller to larger. So just remember that the ratio of the perimeters is our single one, and we're going to actually start with the area ratios. So again, we're going to go small to large. So we have 2 areas, which are 36/144, and this is a squared to b squared. So to convert that, we have to square root them. So that gives me 6/12. Let me just double check that real quick, but I'm pretty sure we're right. And that can reduce down to 1/2. So that's my a to b. That's my final answer. 2 rectangles with 50 to 72, so we take 50/72 is my a squared to b squared. Now these aren't perfect squares, so what I'm going to try and do is I'm going to try and reduce first and see if maybe I'll get perfect squares here. Doesn't always happen. Divide by 2, I'd get 25 on top, and 72 divided by 2 gives me 36, so I get 25/36. So it's still a squared to b squared, but now I can square root them really easily and get 5/6 as my a to b. So a lot of times you want to look out for those, what's it called, perfect squares, so we can get our answer. Okay, the area of a regular octagon is 45. What's the area of a regular octagon with 1/3 the side length of the larger? Okay, well this 1/3 right here is actually giving me my A to B ratio. So this is my A to B is 1/3. So that means if I square them, I'm going to get my A squared to B squared term, which is going to be 1/9. So I can take 1/9, which is small to large, so 45, the area of the regular octagon with sides 1/3 the length of, actually, what is the area of a regular octagon with 1/3 the side length of the larger? So we're looking for the area of the regular octagon with 1/3 the side of the larger. So that means this must be the larger. So we're going to put 45 down here, x up there, so we're finding the smaller one. Cross multiply, we get 45 equals 9x. And 9 goes into 45 how many times? 9 goes into 45 how many times? 5. Mrs. Smith with the math. By the way, Mrs. Smith here, not really paying attention, but was able to throw the answer out to us of 5 feet. That's when you know you found a winner, everybody. When your girl can just, not even paying attention, can spit out a good answer. All right, moving on to the next one. Should we try and catch her off guard again? We'll see. All right, the longer base of a right trapezoid is 12. The longer base of a similar right trapezoid is 30. So I'm already going 12 to 30 because they're in the similar spot. The area of the smaller is 20. What's the area of the larger? So we're trying to find the area of the larger. So we got 12/30, which is my A to B, but let's simplify that. 12 and 30. What goes into both 12 and 30? 3 does go into 12 and 30. I wish there was a bigger number that went into 12 and 30. I'm thinking 6. That's great. Thank you, Mrs. Smith. 2 and 5. There's my A to B. Okay, 2/5. Again, since we're dealing with area, I want to convert this into A squared to B squared. So if I square this, we get 4/25. So I'm going to use this. And then they said the area of the smaller is 20, so that's going to go on top, larger on the bottom. We're going to cross multiply. We get 4x equals 20 times 25, which is 500. Divide by 4, and x is going to equal 125 square feet. Find two similar parallelograms, have areas of 125 and 80. The height of the larger parallelogram is 10. What is the length of the base of both parallelograms? Okay, so this one is quite challenging. So let's go ahead and see if we can figure it out. So we have our areas. So let's go ahead and take those two. I'm gonna continue my smaller to larger strategy here. And this is my A squared to B squared because they're areas. So first I want to see if I can simplify that. And so I'm looking at this and I'm thinking, okay, what's gonna go into both? And I think 5 definitely goes into this. So let's try 5 first. So 80 divided by 5 is 16. Oh my gosh, we are lucky. And that's going to be 25. So the reason why I say I'm lucky is that 16 and 25 are perfect squares. So if I square root them, I'm going to get 4 and 5. So that's my A to B. That's really important because it says the height of the larger parallelogram is 10. Now it says what are the lengths? And let's hold off here for a second. Let's find the height of the other one. So the 10 is the larger, so we're going to put that on the bottom, x on top. Let's cross multiply. We get 5x equals 40. X is going to equal 8. So let's do two equations. So we have a small parallelogram and we have a large parallelogram. We know that the height of the large is 10. We just found the height of the other, that's 8. Okay? We know that this one should equal an area of 80 square centimeters, and this one should equal 25 square meters. So the question is, what are the lengths of both bases? Well, I'm going to have to do 10 times x, right, which is the length, and we're going to do 8 times x, which is equal to this. So this one's really easy. 8 divides into 80. We get x equals 10. So one of my lengths is going to be 10. And then we divide this by 10. And I get 12.5 equals the other length. Now let's just make sure that those are in the same ratio. So 8 to 10, if we were to do that, 8 to 10, we get 4 over 5, right? 4 over 5 was my A to B. Is 10 over 12.5 the same? And so I'm going to use my really cool calculator. So I did 8 over 10. It's still 4 to 5, which should be my ratio or my scale factor of my single term. Let's try 10 over 12.5. Now if this ends up being 4 over 5, we are solid. And guess what? It does. So this holds true. And we want the ratio to be the same for single dimensions. Length and height are single dimensions, just like perimeter. So on our little cheat sheet, a lot of times perimeter ratio, scale factor, sometimes we even say, height ratio or length ratio. Again, anything that's one-dimensional. Height, length, perimeter, they're all single dimensions. Area ratio, 2 dimensions, and we'll eventually get to volume, which is 3 dimensions. Alright, so those are our 2 answers. A team is excavating an archaeology site. The original plan was to excavate a rectangular area 35 feet long by 25 feet wide. Instead, the team decided to excavate a similar rectangle that's 50 feet wide. Find the length and the area of the new rectangle. Okay, so we want to find the wide to wide. Okay, so that right there is going to be our ratio. So we're going to do 20 to 50. So that should be my A to B. Let's simplify that. Pretty easy to simplify. We just divide by 10. We get 2 over 5. Okay, 2 over 5. Now we can find the area of the first one. So we have 2 rectangles. So we have the original plan, which is going to be 35 times 20. So the area of the original is 35 times 20, which is going to be 700 square feet. And then we want the new plan. Okay, well the new plan, instead of 20, it's going to be 50, but we have to find the other one. Okay, so the easiest way to do this is to actually go ahead and use our scale factors. Okay, so this is our perimeter, our scale factor, if you will, 2 to 5. Let's find our area. It's going to be squared, so we're going to get 4 over 25. So you get 4 over 25. Now 700 is the original one, which is 20. The new one's going to be 50, which is going to be much larger. So 700 has got to be the smaller. So let's find the smaller. We're going to cross multiply. You get 4x equals 700 times 25. So a really large number. 17,500. Divide by 4, x equals 4,375. So that's going to be what the area of the new one is. So they're obviously doing a lot more work. But I don't know what they're multiplying by right here. So to solve that, so again, we wanted to find 2 things. Find the length and the area. Well, we just found the area of the new rectangle. It's right there. Now we want to find the length. Well, if I don't know this, I can solve this as an equation. We'll put in a variable. We'll call it L for length. So if we divide by 50, we should get our length. So our length should be 87.5 feet. And that is the length of our new shape. So there's our 2 answers. Okay? 15, 16, 17, 18, 19, and 20 are factoring problems. I'd like you to just try your best on those. I'll give you a little bit of a hint. X factor on This one, these two, we're going to have to take a different approach, which is going to be a little bit more challenging. And same with these two and this one. So try your best. I'll give you a couple of hints. Difference of perfect squares, and also factor by grouping. Okay? This is, again, just a review. Alright guys, thank you so much. We'll see and chat with you guys next class.